topic for the paper is efficient approximation of certain and possible answers for ranking and window queries over uncertain data. Uncertainty is everywhere. Uncertain data can be caused by measurement errors, data cleaning process, and missing data in source. For example, predictions on future position and size of a storm is uncertain. We observe that an important class of query, including top K, ranking, and window aggregations, are widely used, but rarely supported in most of the uncertain and probabilistic database systems. So in this work, we propose semantics for order-based operations over uncertain data by providing under-approximation of certain answers and over-approximation of possible answers as part of the result. Incomplete databases that are used to represent uncertain data is a set of possible words where each possible word is a deterministic database. For instance, we have 4 possible words describing the latitude and radius of the storm. If we ask a question to the incomplete database, what are the IDs of storms with radius larger than 20? Then it is equivalent to run the query on every single possible word. Certain answer is answers that exist in every possible word, and possible answer is all answers that exist in at least one possible word. In this case, S2 exists in all possible answers, so it's a certain answer, and S2, S3 exist in at least one possible word, so they are possible answers. Existing work solving uncertain sorting problem often has high computational complexity, and often incompatible with uncertain data model for other query classes, so user cannot run incomplete queries on top of the sorting result. For window aggregation queries, to the best of our knowledge, only sampling-based incomplete database approaches are capable of handling it. However, sampling-based approaches can only provide under-approximation of possible answer and over-approximation of certain answer which does not have any correctness guarantees. For example, the purpose of certain answer is that user can totally trust those results, but an over-approximation of it is not trustworthy anymore. Our previous works, we proposed an uncertain data model called AODB that bounds uncertain data using under-approximation of certain answers and over-approximation of possible answers using both row and attribute level uncertainty. User can map different kinds of incomplete database models into AODB that bounds the model, and the bounding effect is preserved through queries, supporting full relational algebra including aggregations, and AODB is proven to be theoretically and practically efficient. An example AODB can be visualized as shown above. It uses ranges to encode highest and lowest possible values for each attribute, and highest and lowest multiplicity for each tuple. A possible word can be extracted by assigning value in each range. For example, if we pick value indicated by the arrows, the possible word below can be extracted. AODB also encodes a selected guess word using the value in the middle. AODB underestimates certain answers, meaning all tuples from lower bound multiplicity must exist in all possible answers, and over-approximates possible answers, meaning all tuples from all possible words can be found using upper bound multiplicities within the attribute range. For this work, our main contributions are development of sorting and windowed aggregation semantics on AODB uncertain data model, and prove the semantics to be bound preserving. We implement the semantics in GPROM, which is a SQL rewriting-based database AODB resides on, and also native one-pass algorithm implemented directly on Postgres, which shows that our approach is theoretically efficient and practically efficient by comparing with other approaches. For deterministic sorting, the sorting order is physically applied to the data as the output since there are only one physical sort order. However, uncertain sorting needs to model multiple sort orders, so instead of physically sort the data, we need to treat the sorting position as data such that sort position is sorted as a new column in the result. For example, S2 can have latitude of 38, and it is possible for S1 latitude to be 34 or 40, which make S1 could either sort it before S2 or after S2. So we use ranges on possible positions as a sorting result to model this effect, where lower bound is the number of tuples certainly preceding, and upper bound is the number of tuples possibly preceding. We ignore selected guess value, which are the values in the middle for the later examples, because the selected guess answer is just deterministic query processing over all the middle values. The semantic for our uncertain sorting is to count minimum and maximum number of preceding tuples for each tuple. Here we try to find the sort position for S1. There are no tuples certainly in preceding of S1, even if we choose smallest value for S1. So S1 gets a position lower bound of 1. For S1 upper bound, we count all tuples can potentially in preceding of S1 using the upper bound of S1. In this case, both S2 and S3 can be sorted before S1 using their lower bound value. So the upper bound position for S1 is the sum of multiplicity upper bound of S2 and S3, which is 4. Lower bound for S2 can be computed in a similar way. In this case, although S3 is guaranteed to have lower value than S2, but S3 might not exist given lower bound multiplicity for S3 is 0, so S2 still get lower bound position of 1. And all tuples can precede S2, so S2 get upper bound position 4. And similarly, S3 can get the lower bound of 1, and upper bound 2 since only S1 may precede S3. And here we notice the position for S3 did not count for its own multiplicity yet. So we solve this by dividing multiplicities of S3 and assign incrementing position result to each of its multiplicities. We then discuss window aggregation semantics. For uncertain window aggregation, the challenge is that due to uncertain sort order, the window size will no longer be fixed when considering tuples could possibly be in the window, depend on the sort order, and also ranges on the value we're aggregating on will affect the aggregation result. Consider example, try to find the largest radius between current and next two storms with larger latitude value for each tuple. Again, we ignore selected guess value in the middle since it's deterministic. We demonstrate how to get the result for tuple S4. We first sort all tuples using our uncertain sort semantics, which add a position column to the input AUDB. Then using the possible position between S4 and other tuples, we can reason about the window. The certain window is tuple that must be into following of S4. In this case, S3 with sort position 2 and tuple multiplicity certainly 1 is in the certain window. S2 is not in certain window since the position can be 4, which is not within 2 following of 1, and S3 with position 3 is not certainly in window since the tuple is not certain. We can now aggregate over the certain window to get a lower bound maximum aggregation using the lower bound radius result, which is 17. The possible window is tuples can possibly be in 2 following of S4. In this case, all tuples are possibly be in the window. So upper bound result is a maximum of the radius upper bound over all possible windows, which is 25. Notice when we get certain and possible windows, the aggregation must include all tuples from certain window, but will fill up the rest of the window size with tuple from possible window only if the tuple can contribute to the bounds depending on the aggregation function and lower or upper bound. Specifically, the lower bound for max do not want any possible tuples, and upper bound for max want all possible tuples. Oppositely, min want all tuples for lower bound, but no possible tuples for upper bound, and sum only need possible tuple with negative aggregation value, while upper bound only need possible tuple with positive value. There are some challenges when we implement these semantics by rewriting the query, since we need to sort on both lower and upper bound values. We use tricks from temporal database that split intervals into endpoints and process all endpoints in order. However, this duplicates each tuple into 2 endpoints, which introduce redundancy in performance overhead. We realize that we are facing the limit of SQL queries, so in our Postgres extension implementation, we use a one-pass algorithm that stores input only once using heap to maintain sort order over active tuples. And for window aggregation, we need more than one heaps to store reference to tuples in different states. The main idea of the algorithm is to first determine the lower bound of the sort order for input tuples, then retain tuples in the heap until their sort upper bound can be determined. The algorithm expects the input to be sorted on lower bound attribute value we are sorting on, and we record a watermark for number of tuples we popped from the heap and number of tuples we pushed into the heap. Starting from S1 with lowest lower bound value 30 and empty heap, we know no heap is popped yet, so we push S1 into the heap, and we know the lower bound position for S1 is 1 since S1 has no guaranteed precedings, and we increase the push count by 1. Then we get by S5 with lower bound value 33, which is smaller than the minimum upper bound value in the heap, which is 40. So the value range of S5 overlap with all tuples in the heap, so we push S5 into the heap. And S5 becomes the root of the heap due to the lower value it has on its upper bound, and we increase the push count. Now we get S2, which with lower bound value 38, which is larger than the minimum upper bound S5 in the heap, which indicating S5 is guaranteed to be in preceding of S2 and all tuples after S2 since lower bound value for incoming tuples will only be larger. So we can pop S5 by assigning push count to its upper bound position, and we increase the pop count indicating all tuples read afterward must have one tuple which is S5 as its preceding tuple. And now since our tuples in heap is overlapping with S2, we push S2 to the heap. S2 is in heap will have lower bound position of 2 due to the increased pop count, and we increase the push count. The algorithm will continue until all tuples have been processed, or we get k tuples for the top k. For complexity of this algorithm, we need n log n to sort the input, and need log n time to perform insert and delete heap operation for the total of n tuples, resulting in n log n time in total. And also big O n time for the memory complexity in case all tuples are in the memory. For window aggregation algorithm, we use similar ideas. This time we need more data structures to bookkeep tuples in different states. We need to catch small amount of tuples that's certainly in the window, which we can manage by iterating through them. But we cannot do the same for possible window, which potentially can be large even for small window size. So for possible window, we use heap to decide which tuple to pop when it's no longer in the possible window. This figure demonstrates the current and 5 preceding certain and possible window for tuple S, where the axis denotes the sort position. In this case, T1 is in possible window, T2, T3 is in certain window, and T4 is not in the window of tuple S. The challenge we face to use possible window is that we need possible window heap to be ordered on sort position of the order by attribute, so we can maintain it similar to the sort algorithm. But in order to calculate the aggregation result bound from possible window, some aggregation function like sum needs the tuples in window to be ordered by the attribute we are aggregating on, so we need to maintain 2 orders for the same set of tuple. We can use one heap for each order, but when we pop the root on one heap, we need to search that tuple in other heap, which costs linear time, which is slow. So instead, we use a connected heap where we make each tuple point to positions of all heaps they are in. So when we pop in one heap, we can pop all the tuple from all heaps in log n time. More details about the window aggregation algorithm are described in the paper. The window aggregation algorithm has runtime complexity of big O Wn log n, where W stands for the window size and worst case of keeping all tuples in memory. We run our experiments on a 2x6 core CPU machine with 128 gigs RAM, and we measure average of 10 runs. For sorting, we compare with sampling and sorting approaches to return exact bounds. For window aggregation, due to the lack of competitors, we compare mostly against samplings. For experiments on sorting performance, we compare our approach with exact bounds that are as tight as possible, but those approaches are generally slower by orders of magnitude. For our approach, the green line is our rewriting-based SQL approach, and the red line is the native algorithm approach. Our rewriting approach is slightly slower than the blue line, which is a sampling-based approach with 20 samples, and our native algorithm is slightly faster than sampling-based approach with 10 samples. For window aggregation, exact bounds are too expensive to compute. In fact, the execution never ends for hours, so we did not include it in the result. Our rewriting approach behaved bad due to the range overlap drawing effect. Even for the orange line, which we use index to speed up the drawing, it's still relatively slow. Our algorithm in red line, on the other hand, behave very close to the sampling-based approach with 10 samples. For some quality measurements on real-world data, we measure the over approximation of our bound, which is accuracy, and the under approximation of sampling-based approach, which is recall, if we bound on the result of the samplings. If we compare these bounds with the ground truth bound computed by expensive approaches, although it is not fully fair to compare recall and accuracy, our results are closer to the ground truth than the result from 20 samples, even though our time performance is close to the performance of 10 samples, which is way faster than 20 samples performance. For conclusion, we extend AODB for order-based operations which preserve the bounds, making uncertain sorting working in a closed system, and we being the first windowed aggregation approach for uncertain data. We showed that our approach is theoretically and practically efficient with p-time complexity and reasonable overhead over deterministic query processing. For future works, we want to use uncertain data models beyond boxes for improved accuracy. We can potentially develop disk-based variants of the one-pass algorithm, and we can look into uncertain recursive queries and uncertain iterative computations. And this is the end of the presentation. Thank you.